let's dive inside LLMs. Here I have a definition of GPT-3 that you've probably seen before. It's commonly used. GPT-3 is an LLM with 175 billion parameters spread across 96 layers, trained on 300 billion tokens. Okay, what in the bleep does that mean? It's a lot of big numbers, and it's not really that intuitive, right? Well, I want to break this down so that you can understand how an LLM works on the inside. So that definition that we just talked about, that's in the top right corner there, as you can see. And I'm going to focus just on the purple part here for now. 300 billion tokens. Okay, well, what are tokens? That's something that we've learned a bit about already, right? Tokens are words, kind of. They're essentially the words that the machine understands. It's broken down the words into tokens. And 300 billion tokens? That's about 45 terabytes of text data. And by text data, I mean that's all books and articles and websites from the internet. All the stuff that OpenAI could get its hands on. And then it took that text data, tokenized it, turned it into tokens, and trained the LLM on it. And that includes all sorts of information out there. So frankly, if you have a blog post or a Twitter account or things like that, you probably have information, probably have text data that was used to train these GPT models on. So congratulations, you have contributed to the advancement of artificial intelligence, whether you know it or not. Nice work. Okay, joking aside, now we understand what that 300 billion tokens in the definition means, right? It's basically about the size of the text data that the large language model was trained on. And obviously, more tokens generally means a better model. I'm going to caveat that very quickly because it is a very general rule. More tokens alone is not enough, as we'll talk about. All right, so we've just learned about the 300 billion tokens part of this definition of an LLM, right? Well, let's move on to the other parts. Specifically, 175 billion parameters spread across 96 layers. This is where we start to really get into the nitty-gritty. The tokens part was too easy. You already understood that, right? Or if you didn't, you had a hint about it. But this talk about parameters and layers, this isn't clear. So let's make it clear. And to do that, I want to go on a little bit of a side quest here and talk about your brain. That's right, the thing that's sitting in your noggin right now, listening to me. And to be clear, this is very relevant because these large language models are a neural network, which has some similarities to your brain. So that's why I want to go on this little side quest first, because it's going to help you understand later on. So let's imagine you're trying to think of this funny balloon that you remember seeing at someone's birthday party, or maybe it was your own birthday party. You can't remember exactly what it said, but you're like, oh man, that was a really funny balloon. Here's a picture of that balloon for the record. It says, just let me know how old we're telling people you are now. Very funny, right? Okay, give me a break. It's kind of funny. There's not that many funny balloons out there. This is the best I could find. So you're sitting there thinking, what did that balloon say? What did it look like? And you're struggling to figure it out. Well, what's happening in your brain when you're doing that? Well, let's take a look. So here we have a bunch of neurons in your brain. These are cells in your brain that take in and transmit information. And there's tons and tons and tons of them in your brain. And then here you are thinking, what did that semi-funny, kind of funny balloon say? Well, when you think that, a little electrical signal is sent to one of your neurons right here. And it activates, in this case, turns pink. And then that neuron sends out information to the neurons it's connected to. And it turns some of them pink. It activates those neurons. And then those neurons send out information or a signal to the neurons that they are connected to. And it turns some of them pink. It activates them. And what do you think happens? That's right. Those activated neurons send out a signal or information to the neurons it's connected to. And oh, what's this? We just activated the funny balloon neuron, the neuron that represents that balloon in your brain. And then the light bulb goes off and you say, oh, that's right. That's what the balloon said. And that's what it looked like. And so that's what's happening when you're struggling to think of something, right? What's happening is you're activating neurons. You're sending electrical signals to neurons, which is causing the surrounding neurons to go off, which is causing those surrounding neurons to go off. And then hopefully, if you think about it long enough, the neuron of the thing that you're trying to remember gets activated as well. And then you're like, oh, that's the thing. That's where I left my keys, whatever it is. How wild is that? And now if you're an astute observer, you may have noticed not all of these neurons are turning pink. You can see here, it's sending a signal to this neuron here, but it stayed purple, right? And that's happened a few times here. That one stayed purple even though it received a signal. This one stayed purple even though it received a signal. What the heckin' is going on here, huh? Good question. All right, so to show you this, I'm going to bring in this chart right here. And let's explain this quickly. So what do we have along the x-axis here? This is time. And along the y-axis, we have energy. Okay. We also have this dotted line here called the threshold. And then we have the resting potential. Okay. So what's happening here? What we're going to see in a moment is we're going to see a line start going from left to right here, below the threshold. And this is the resting potential of the neuron. And you can think of the resting potential as like a base level of energy that the neuron always has. It's kind of like you, right? You have a base level of energy. You always have some energy in your body, but that energy level can go up. And once we see that resting potential go across, eventually at a certain point in time, it's going to jump up above the threshold. And if it does, the neuron is going to activate. Got it? All right, so let's see this in action. So we've got the resting potential there, and then, oh, it went above the threshold. And what happens when its energy levels, because remember this y-axis is energy, goes above the threshold? Well, then the neuron activates. Let's see that again. And up and down. Okay. So what's causing the energy level to go up? Well, it's this signal that it's receiving from the other neurons. This neuron is sending signal or energy to this other neuron, which means it's chilling out at its resting potential, and then it's like, oh, bunch of energy, and it crosses that threshold, and boom, that neuron is activated. How cool is that, eh? This is going on inside your brain right now, all the time. And so what do you think happened with this neuron, right? That was the question that we had at the beginning. It stayed purple. It didn't activate. Well, its chart would look something like this. It's chilling out its resting potential. Oh, up a bit. Oh, but doesn't cross the threshold, so it never activates. Even though it received energy from this neuron, it wasn't enough energy to get it to go over that threshold. And by the way, what this means is that if you want to be better at something, you need to strengthen the neurons and the connections between them. If you strengthen your neuron and the connections that it has, then you make it so it's easier for it to activate. Maybe you're lowering the threshold, or you're creating more connections so that it's able to take in energy from more neurons. It's more likely to receive energy from more neurons, right? If it has more connections. So that's what you're doing when you're learning. That's why it's helpful to learn something and understand how it connects with everything else, to repeat something, to practice it so that it is a stronger neuron and doesn't require as much energy to reach that threshold. Wild stuff, eh? And by the way, if you don't believe me, here is an actual video of a neuron in a brain seeking out connections. Imagine this is your brain right now, and that's you practicing something. That neuron represents what you've learned in this lesson, and it's trying to find connections. It's trying to reach out. You can see all the electrical signals flying through these connections here, right? And unfortunately, it looks like that neuron did not quite make the connections it needed to. So I blame you for that. You should have been thinking harder on it and made it stronger. Just kidding. Don't worry. You're doing great. Okay. So this has been quite the tangent. And at this point, you're no doubt saying, Scott, what is going on here? Is this a course about my brain, or is this a course about large language models and artificial intelligence? Well, right now is when it's going to start making sense, how it's all connected. Because this is what the inside of a large language model looks like. And what's the first thing you notice? It kind of looks like all those neurons that we were looking at in your brain, right? There's a bunch of neurons and they're all connected. Well, remember what I said at the beginning of this lesson. Large language models are a neural network. In other words, they're a network of neurons, very similar to your brain. In fact, the creation of them and the design was inspired by how your brain works. So let's break down what's going on in this picture. Here we have neurons. Each one of these dots is a neuron, okay? And they're divided into different layers. They're structured. We have an input layer here, and then we have layer 1, layer 2, layer 3, and an output layer. Okay, so right away, we can start to break down this definition, right? We can see what we're talking about when the definition of GPT-3 says 96 layers. We've got 5 layers here. GPT-3 has 96. Okay, and then what about the 175 billion parameters? Well, parameters is sort of an umbrella term that encompasses a bunch of other things, specifically calculations that are going on inside this large language model. There's 2 key types of parameters I want you to know about, though: weights and biases. The weights are these lines in between the neurons. You can see every neuron is connected to all the other neurons in the next layer, right? You can see this neuron right here. It's got a connection, that line, to this one, and to that one, and to this one, and to this one, and to that one, and so on and so forth. This one's connected to all of these as well. Each one of those lines is a weight, which, again, all you need to think of that as is a calculation. A weight is a calculation. At each of these neurons, there is also a bias, which also you can just think of as a calculation. So if you added up all the weights, all the lines between these, and then you added a bias that occurs at each neuron, you'd get the total number of parameters inside this large language model. And as you can see from the number up here, that's a lot of parameters that is in GPT-3. There's a ton of calculations going on inside of these models. It's really incredible. Now, I know this has probably been a little bit confusing, so let's run through a very simplistic example to make it make sense. So let's say at the input layer, you start with the number 100, right? You can see it right there, 100. Then you have a weight, which is a type of parameter that takes that number 100 and modifies it with some calculation. In this case, the weight is 0.5. So you take 100, multiply it by 0.5, and you now have 50. And then that neuron continues to pass the information here to the next neuron, and then a bias is applied. This bias is plus 10. So what do we have now? Well, we have 100 times 0.5, so 50, plus 10. We now have 60. Okay, so this neuron now has the number 60. And just like the neurons in our brain, where they had a threshold, an energy threshold that needed to be met, in this case, these neurons essentially have a number threshold. The number threshold is 50. So this neuron passes the threshold, which means it can fire and send information off to all the neurons it's connected to. In this case, I just want to keep it simple again, so I'm just going to show you the calculation of one neuron that it sent it to. So now we're taking the number 60, and we modify it by the weight, 0.7, which gives us 42. And then we take the number 42, and then we apply the bias to that, which is minus 7, so that gives us 35. And so now this neuron has 35, but the threshold it needs to meet is 70. So, okay, this neuron is not going to fire. Or in fact, what it does is it ends up passing on the number 0 to the next neuron. But there you go. That is a very simple example of how these parameters work. These weights and biases work between all the neurons and all the layers in a large language model. But now you're probably saying, what does it all mean? What is the point of this? I don't understand. I thought these things were predicting tokens. I thought they were giving me words. Well, let's convert these numbers now into tokens. Let's take a look at what it actually looks like. Here we have you going into ChatGPT and you're typing in Mary had a. That information is put into the input layer, right? And then these tokens are taken through and all these parameters are going to whirl around and calculate things and adjust the numbers. And then what is it going to spit out? It spits out its prediction for the next most likely token, which in this case is little, right? Mary had a little. And then because these models are autoregressive, which is something we've talked about, but we're going to talk about it more later on, it's actually going to take that new token, that output token, little, and it's going to add it over here back to the input layer, right down there. And then it's going to rerun all of these calculations again, and blah, 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 blah. And then what's it going to spit out? Its prediction for the next most likely token, which is lamb. Mary had a little lamb. And then it'll continue going and going and going. How wild is that? Well, it's a rhetorical question because it is very wild. And in fact, it's so wild that we don't really understand what's going on in these layers. In fact, these middle layers here, everything but the input and the output layer, all these layers are actually called hidden layers. Because sure, we can look at the weights and the biases. We can see, oh, okay, it's going to take the number 100 and it's going to multiply it by 0.5, and then it's going to apply a bias of -7 or whatever. But we don't know why that works. There's this whole field of artificial intelligence called mechanistic interpretability that is trying to figure out why, when you take these tokens and apply these 175 billion different calculations, you get seemingly the correct next token. Whew. Very, very cool stuff. And now you understand how it all works better than 99.9% people out there. Back to the focus here. This definition, right? I wanted you to understand what this definition means because this is a common way to describe large language models. This is the definition for GPT-3, but you're going to see similar definitions for all the other models. This space is moving very quickly. New models are being released all the time. And now you're going to be able to glance at those models and say, oh, okay, I understand what that means. I understand how much bigger or smaller or different this model is from other ones. And let me show you an example of that right now. We have Llama 2. This is Meta's open source model. And this is the common definition of it. Llama 2 is an LLM with 7 billion parameters spread across 32 layers trained on 2 trillion tokens. So you can see here, it's got far less parameters, significantly less layers, but a lot more tokens. It was trained on a lot more tokens. And so like everything, there's trade-offs. No two models are the same. What's interesting to understand is that there is a scaling law with large language models that says the more tokens you train it on and the more parameters you have, the smarter it gets. And that is basically a strong correlation. These models get better and better the more tokens you train them on and the more parameters they have. So in general, you're going to want to use models that have the most parameters and the most tokens. Phew, all right, that was a lot of information, but now you really got a peek inside of LLMs and are able to understand what they really are. That's pretty exciting. So nice work. I'll see you in the next lesson.